Hi guys, welcome back to my channel. So today we're going to talk about exponential functions. I want to use an example to illustrate. So a bacteria doubles every single hour. If the petri dish will overflow when the population of bacteria reaches 50,000, then how long will it take to fill the petri dish? So assuming that I start off with one bacteria in my petri dish, that number will then double every single hour. So this would be, I would have 2 bacteria after the first hour. After the second hour, I then would have 4 bacteria. And then after the third hour, I would have 8 bacteria. So we can actually model this growth using a table. So all I've done is I've just gone ahead and I've filled out each of these values. So I'm assuming X here is going to be my axis for time. And that's going to be in hours. And then Y is going to be the population of the bacteria that I have. And what I want to try to determine is I want to try to determine when that number is going to reach 50,000. So I could continue to double and double and double this number until I actually found the value that I wanted. So let's go ahead and see if we can determine this number using this method. So I've gone ahead and I've actually calculated all of the values until I actually found one that went over that population of 50,000. So somewhere between the 15th and the 16th hour, the bacterial population is going to overflow. So I think that probably you can recognize that there's going to be a simpler way to do this rather than trying to double this value each and every single time. So this goes back to the primary function of what an exponential graph actually looks like, which is y is equal to a to the power of x. And so in this case here, we've defined our x as our value for time, and we've defined our value for y as our population. So how do we then find this value of a? Well, this is actually really simple. So what I can actually do using my table, I can see that for each value of x that's going up by 1, and again, this is going up by 1 and going up by 1, so that's really important, that this value for y is doubling every single time. And so since this value is doubling every single time, we can write this as 2 to the power of x, because we are repeatedly multiplying this number here too. So we can write this formula as y is equal to 2 to the power of x. Let's try graphing this function and let's see if that would help us to find this value a little bit quicker. So I've gone ahead and I plotted y is equal to 2 to the power of x in Desmos, and this is the graph that I've gotten. And so what we could do, we could probably see now that it's going to be a little bit easier. Let's do this in a red color. If I was to try to determine at what time the population would reach 50,000, and this is just being pretty rough using our graph to help us to estimate this value. So making sure I get this right on the line here. And again, we can see that this is close to somewhere between the 15th and the 16th hour. So this is just a little introduction to exponential growth and how exponential growth actually works. And we can see now the shape of the curve that's actually made by this function. And it's really interesting, I think, with these exponential graphs, because we start off with quite a flat curve, and so it can appear that nothing is really happening. And then all of a sudden we see this big, massive jump. So I encourage you to go have a look on Desmos, type this into Desmos and see what you get. Even if you tried plotting some of the points to see what the function of this curve actually looked like, to prove to you that yes, y equals 2 to the power of x isn't appropriate for this function to this curve, and just to have a go for yourself. All right, guys, I'll see you in the next video with some questions and solutions for some exponential growth. See you in the next one. Bye, guys.